Continuing our discussion of MOSFETs in section 10.3, and we're looking at MOSFET amplifiers. The three basic amplifier configurations discussed for bipolar transistors and JFETs have MOSFET equivalents. And we're not going to go into all of them, but we'll just say that they do have equivalent circuits. Amplifier biasing, and this pertains to amplifiers. Any of the MOSFETs can be used as linear amplifiers. They must be biased so that majority current carriers flow from, from source to drain. The gate source capacitance is biased such that the transistor is operating midway between cutoff and saturation, as with all transistor amplifiers. So remember, we had cutoff, we had saturation. This represents basically the on and off positions of the MOSFET, and then in between those is where we could have linear operation. Remember that when you have linear operation, you will have an input, and the output will have the same shape as the input. And if you were allowed to go into saturation or into cutoff, it will no longer retain the same shape as the input. Once properly biased, an AC signal is applied between gate and source, adding and subtracting from the DC bias. MOSFET amplifiers have a 180-degree phase shift between input and output. This is just like we did with bipolar. Most notably, MOSFET amplifiers have, notice this, extremely high input impedance. Frequently, this is way into the megohms of impedance. And this is good because remember when we talked about the input impedance, that this allowed the amplifier to capture most of the incoming signal. Okay, signal response. A common source amplifier using an N-channel depletion mode MOSFET. So here we have an N-channel depletion mode MOSFET. With an input signal, the current through the MOSFET will vary, causing the voltage across RD to vary, thus amplifying the input. And this is actually the way that all amplifiers work, is that you have an input signal that comes in. The input signal, in this case, goes through the depletion mode MOSFET. The AC signal will cause the current to vary through the transistor, and that current will be passed through here to RD. That changing current will cause this voltage to vary, and so the output here will be impacted, and thus we'll have an amplified signal. Now, we have a coupling capacitor here. The coupling capacitor is here to simply remove the DC level, so that when it goes to the output, it is simply pure AC. This is a common source amplifier. Now this is using a P-channel enhancement mode MOSFET, and you'll notice the arrow is pointing in the direction that indicates that it is a P-channel. Notice we have a negative voltage, which is characteristics of P-channel devices, and again we have the same basic behavior. An input signal is applied. The current through the enhancement mode MOSFET is going to vary based on that input signal, causing this output to vary, and thus we will have our output through the coupling capacitor. MOSFET characteristics. Because there are fewer sources of recombination, as in bipolar transistors, MOSFETs have very low noise levels associated with them and are ideal for early stages in an amplifier. Okay, what's this mean? Because there are fewer sources of recombination. Well, with bipolar, remember we had our material N, P, N, and we had the recombination as electrons pass through the P material and then to the N material. And though this seems rather insignificant, this is a source of noise when electrons pass through and they go through the process of recombination. Recall in a MOSFET type device, or with a FET, we go from source to drain, and we don't have any recombination. We just have the restrictions that are placed on this material to cause current to vary, but the electrons stay in the same material all the way through, so there is no recombination, and this does reduce noise. This makes them ideal for the early stages in an amplifier. Now, one example is that in a television receiver, for example, has an antenna, and when it receives a signal from that antenna, it is a very, very tiny signal. And it is very common that MOSFETs are used at that level when the signal is very small to be able to amplify the signal without adding any noise to it. Okay, MOSFET handling procedures. This is a very interesting subject. Because of their construction, MOSFETs are extremely sensitive to static voltage charges and must be handled carefully at all times. Otherwise, they will be destroyed. And this brings us to the subject of ESD. I suppose I could teach an entire chapter on this subject, but I just want to mention it at this point, that MOSFETs are what we call ESD sensitive, meaning that if they're exposed to electrostatic discharge, it can potentially damage the device, and so they have to be handled very carefully, especially when you are repairing a device where a MOSFET needs to be replaced. ESD stands for electrostatic discharge. ESD is developed when two insulators are rubbed together, and some examples that you might recognize is, for example, in a clothes dryer. When clothes are being are dry and you go to take them out of the dryer, you may have experienced the popping and you sense the electrostatic voltages as you're pulling the clothes out of the dryer. Well, that's an example of ESD. Shoes, if you're walking along on a carpet and you're rubbing your feet on the carpet and then you go touch a doorknob, you might experience a little lightning bolt, and that would be another example of ESD. Tire rubbing against pavement. Have you ever been driving a car, you get out of the car, you're standing on the ground, and then you go to close the door, and as you touch the door, you get shocked? Well, the reason for that shock is that if you're driving down the road and you have the rubber tire, and the rubber tire is rubbing against the pavement, the rubber tire is an insulator, the asphalt or cement is an insulator, and these are essentially rubbing together, and you're having and actually there's a separating going on here as well that's causing the static, and that static electricity accumulates on the shell of the vehicle, and then when you step out of the vehicle and you close the door, you discharge the static electricity on the shell of the vehicle. Another example is helicopter rotors. As helicopter rotors are spinning around, they can develop tremendous amounts of static electricity. Okay, the static voltage can be very high and is affected by humidity, and these are just some ballpark figures, and I'm putting these down because these are commonly used values. And like I say, these values would be typical in high humidity areas. If you were in very arid areas like Phoenix, these values could easily double. So, rule of thumb here is about 3,000 volts of static, you can feel it. At about 4,000 volts, you can hear it. You hear this like with the dryer. And with above 5,000 volts, you can see it. Actually see the little lightning bolt. And in your text, it talks about this value being 10 to 11 kV, which is very probable if it was in a arid environment. Okay, point is that this is where you begin to sense these voltages. MOSFETs can be destroyed with as little as 10 to 100 volts. Now, you will not be able to sense it until it is way above the value where you're looking at potential destruction. So, at any rate, when handling MOSFETs, it is very important to be aware of the fact that these devices are ESD, and usually they have the packaging has symbols on it to indicate that it is ESD sensitive. Okay, summary of MOSFET characteristics. The source and drain terminals connect to opposite ends of the channel material. A depletion mode MOSFET is on with no gate source voltage. Okay, this is the depletion mode. Channel current in a depletion mode MOSFET can be increased or decreased from the no bias condition. An enhancement mode MOSFET is cut off with no gate source voltage. Okay, that's kind of like what we had with bipolar. Is that with no input, there was no output. Okay, MOSFETs have extremely high input impedances or input resistance. A MOSFET can be used in digital applications by restricting operation to saturation and cutoff. Common source, drain, and gates are MOSFET amplifier configurations, and common source amplifiers have 180-degree phase shifts from input to output. And this concludes section 10.3.